So for the dynamic analysis of the 4-bar mechanism, which I started last time, if we were doing static analysis, we would just draw the free body diagrams and then write the equilibrium equations and find the forces. Whereas here we need to do the kinematic analysis and we need to know the masses and inertias. Okay. By the way, in this problem, we assume that we ignore the gravitational forces, which means that the 4-bar mechanism might be on the horizontal plane, for example, so that the gravitational forces do not apply. What do we have to do? In the first place, we have to find the accelerations, angular accelerations of each link, plus we need to find the acceleration of the mass centers. And that's what we did the last time. The kinematic analysis, which is quite involved, gives you alpha 1,3 and alpha 1,4. Alpha 1,2 is given, okay? These two are given, omega 1,2 and alpha 1,2. But you need alpha 1,3 and alpha 1,4. And also we need the accelerations of the mass centers of each link. And we find them through, basic acceleration analysis, okay, and relative acceleration analysis. G4x, G4y, etc. And that's where we have stopped because we didn't have time. We have to continue from here, okay? So we found the acceleration of what is that? Acceleration of G3, okay, okay, it's here, G3 relative to A, X and Y are here. You just have to add them up to get them, and the acceleration of G4 is given here also. They are long expressions, but as I said, when they are programmed on a computer, it doesn't matter whether they are long or not. You can just use them. So after this, what do? We do all this to find the so-called inertia forces. Okay, because there are the inertia forces in dynamic analysis. F2 inertia in the second link is minus M2 A G2, that's all. And T2 inertia is I G2 yes. Similarly, F3I inertia force. There's a minus sign. M3A G3. Finally, F4I. Okay, so once we do this, now we include these in our free body diagrams as external forces, kind of, and then we do static force analysis, but we include the inertia forces. So we draw the free body diagrams now, free body diagram for links 2, 3, and 4. So link 2, let's say link 3 and link 4, let's say. Okay. So what are the forces? Let me just draw them. E1 to X1 is T1, 2. This angle is 1, 2. There is G2. There is the inertia force also. Let me draw it in F2I. We don't, the direction, this force is known, so it doesn't. So these are all the forces acting on link 2. So this was A0, this is A again, and this is B. So what are the forces now? Well, there is a external force here, which is like here F3, or was it F13? F13, I think. That makes an angle of phi. Now F23 is again F23, but it's in opposite directions. So this is F23x and y. Okay. And here you have, this is A, this is B, B, X. Okay, we have, this is, let's say, G3. By the way, we know that this distance between here and here is B3, okay? The point of application of force is at B3. G3 is at distance G3. Anyway, we have the inertia forces. Let me draw those. F3I. And finally, the fourth one. This is again B, and this is 0. Oh, well, coordinates in opposite direction. This has to be downwards because this is upwards. There is the inertia force, whatever it is. F4I. Okay. So this is linked to, this is 3, and this is so we need to write the equations for each of them. First of all, let's check our equations and let's check our unknowns first. G12x, G12y. These are unknown, right? T12 is unknown. F2, 3x, y is an unknown. F2, 4x. These are two unknowns. T14x, T14y. So in total, we have 9 unknowns. Which means that we need 9 equations, and that is exactly what we will have. We shouldn't worry because for each link we are going to have 3 equations. Now we are going to write static equations, okay? That is including the inertia forces. We will write F equals summation of forces equals 0. So we will just can solve from here. Let's write the equations. 9 equations needed, let's say. So let's write them. Link 2. Oh, well, maybe I should just show it here so that the summation of forces for link 2 in x direction is G12x minus F23x now there is the F2 force. We need the x component of that, whatever that is, plus F2 inertia, the x component of it, equals 0. This is known, so it's not a problem. And the summation of forces in the y direction gives G12y minus F23y plus, again, F2i, y component 0. And finally, we need to take the moment of these forces. Well, let's say that for the sake of taking moments, let's say that this F2 makes an angle of alpha, alpha 2, let's say, between the horizontal. Okay. In which case, we can take a moment about A0. There is T12. Okay. A few things. This is 3. And then we can write the same equations for link 3 and 4. Let me check if it is done in your. Actually, it is the same thing, just done over and over again. So it's not really worth writing it. But let me check if your book has it. Yes, it does. They are just regular equations. From which you can solve for the unknown. So we are going to have 3 equations for each link. So we will have 9 equations for 9 unknowns. They are not too hard to solve. They are easier than they look because they are quite sparse equations. That is, they don't have too many variables each equation. For example, the first equation has 2 unknowns, the second one has 2 unknowns, etc. So you can this one has, for example, 3 unknowns. And you can even solve this one without looking at others. So, well, it is solvable, that is. The thing is, the closed form solutions might not be too easy to find, but what we are trying to find, as you remember, was solve for the torque T12 for each value of, let's say, theta12, theta12 from 0 to 2 pi. Okay. Theta12 changes from 0 to 2 pi. As your mechanism changes its position, as you see over here, whatever it is. This is just one position of the mechanisms. For different positions of the mechanisms, those torques are going to change. So you can, well, of course, it's impossible, almost impossible to do it by hand. But if you program it, you can solve for T12 for each position of theta. So that, let's say this is theta12 from starting from 0 to 2 pi, so that you can solve for the value of T12, let's say Newton meters, starting from here it will be some curve like this, for example, so that you can find the maximum value of T12 in this as your mechanism changes its position. Well, the maximum values are important. T12, let's say maximum, it's necessary for, let's say, motor selection. Okay. In order to select a motor for the mechanism, you need to know the maximum torque in your mechanism, well, maximum torque required in your mechanism. And also the maximum power, for example, would be the T12 times omega 12. You can select the motor accordingly by finding the maximum power as well, okay? So if omega 12 is constant, the maximum power is at where the T12 is maximum. So it is quite involved, as I said, but eventually you come up with the solution for the 4-bar mechanism. Okay. Do you have any questions about this procedure? As I said, it is very much involved, but it is straightforward. Another thing is, this is obviously cannot be asked in a midterm, but in a midterm, what we can do is the following, and that's what we usually do. And I will try to solve such problems to you. For example, you can do simplify the problem. For example, a 4-bar mechanism, you can take it as such. In which 2 of the links might have negligible length, let's say, so that you might have M2 equals M4 equals 0, okay? And M3 is not 0, for example. In this case, the 4-bar mechanism analysis reduces to actually only to the dynamic analysis of link 3. In this case, this becomes a problem, for example, that is not impossible to solve as a midterm problem. Do you understand? This is usually what we do when we try to, ask questions about dynamic force analysis. So this is 2, this is 3, this is 4. Any questions about this? Okay, now, if you don't have questions, well, I will solve one more thing, which is the slider crank mechanism again. By the way, I am going to when is that? Next Wednesday, we have a midterm, as far as I remember, which was 5th, right? Next week on Monday, I intend to solve some problems to you. And probably we will finish the dynamic analysis today. So this Wednesday, I am going to start the the next topic, vibrations, but you won't be responsible for that during the second midterm. And then next Monday, I will solve problems. Okay. Again, we have two basic mechanisms. One is the four-bar, the other is the slider crank. Let's look at slider crank here. Somebody asked me. No, you are not responsible for vibrations in the second midterm. And we have A0 G2 is called G2, and A G2 is called G3. The distance of the mass centers, okay? M2, M3, M4, IG2, IG3 are known. And kinematic analysis is done. So we have theta 1, 2, theta 1, 3, and S14. And then omega 1, 2, omega 1, 3, and let's say S14, that let's call it V14. And then we have alpha 1, 2, alpha 1, 3, and A14. These are all known. We assume that these are known. And the problem is given F14 find E12 and reaction forces. Okay. Okay, we need to find the acceleration of the mass centers of each link. Well, links 2 and 3 actually. This is link 2. And this is link 4. For link 2, this is A0. This is G2. And this distance is G2. We have the tangential, we have omega 1, 2, and alpha 1, 2 as well. We have the tangential component of acceleration, and we have the normal component. AG2 tangential and normal. And the angle these make is with the horizontal is theta. This is G2 omega 1, 2 squared. This is alpha. So we just need to make a coordinate transformation to find the x and y components. Let me draw that. This is G2x, and this is. Let me try to write an G2x equal to. Oh, well, minus G2 omega 1 squared now. What is that? Oh, yeah, this angle will be theta 1, 2 as well. So cosine theta 1, 2 minus G2 So this is the acceleration of the mass center of link 2. This is the acceleration of mass center. Well, for G3, it's a bit more involved. I'm sorry, it's not. We are not doing it for bar. So this is A. This is B. This is C. Well, we have AG3 now. We need that. And we need to write a relative acceleration equations. AA plus A relative. Okay, AA is simply well, it is very similar to this. I can write AA as follows. Sorry, that X. Why is that? AG2 is here. Okay. These are the X and Y components. I'm just going to change these G2 terms with A2s. That's all I'm going to do because it's just further distant. This is point A, as you see. So the acceleration of A is acceleration of G2 scaled with A2. So you can write it simply as here. But on the other hand, AG3 is when you have G3 acceleration. This has, let's say, 3, in which case you have AG3 relative to A tangential. AG3 relative to A normal. And this would be G3 times squared. Now we have this angle is theta 3. So you can say that you can use this angle if you like. This is called, you can call it beta or something. This angle will be beta. We will write the x and y components of these forces. One thing is, of course, we assume that omega 1, 3 doesn't matter, but alpha 1, 3 does matter. Maybe we might have to do it upwards. So let's try to do it. Because counterclockwise is positive, so that AG3 is in this direction. Okay, I can write a x component is going to be here beta is pi minus delta 1. Now, these are all wrong, by the way. This is squared. This is now beta sine beta, well, seconds. No, sine cosine. This is gone to 0. Cosine pi is minus, so this will be sine theta 1, 3. So sine beta is sine theta 1, 3. That doesn't make a change. Cosine beta is cosine pi minus theta, which is cosine pi cosine theta 1, 3 minus sine pi. This goes away. Cosine pi is minus 1, so this is minus cosine theta. So you can replace the betas with theta 1, 3s if you like. Doesn't really matter. Okay, once you find these, you have found, this is the acceleration of mass of 3. And also the same for acceleration of the mass center of link 2 is found. So we find it. And then we need to draw the free body diagrams and find the solutions. I will draw the free body diagrams, but I guess we need to take a break. So let me stop and continue after the break. So let me pause. We are recording. Now, the acceleration of mass centers are known. We need to find the inertia forces again. Which is F2I is equal to, or I should say, right. And finally, F4I minus M4. But AG4 is meaningless because this is an object. A4 is the piston, which is an object in translation. And since it's in translation, it doesn't have angular acceleration. So the inertia torque on it is 0. So we don't include that. Okay, we have them. Now we draw the free body diagrams for each of those links. So the crank, which is this is we don't know the direction, but we assume something here. If they come out to be negative, then they will be opposite to what we have assumed. So this is a link 2. For link 3, we assume the opposite direction. This is A. That's all actually. Link 3. There is the link 4. Let me draw it here. And there is the inertia force, which is this. Let me just use another color. This has become very loaded, so it's very slow. So this is for well, at any point actually MA equals 0, but you have to include the inertia. And our unknowns are, let me just check the unknowns. we need G12X, G12Y, F32X, G12, 43X, and G14. That's it seems. For 8 unknowns. Well, it seems we have 9 equations, but no, we have 8 equations actually are needed, and that is, we have no moment equation for the fourth link. Because we are assuming that this is not a rigid, well, it is a rigid body, but it is not making any rotation, so we don't assume anything about it. Well, okay. It is possible to write these equations. Well, and then solve them. For example, again, just as a sample, let me do it for the second link. And let's assume that this makes an angle of alpha 2 with the inertia force makes an angle of alpha 2. This really has become very slow for some reason. It requires a lot of memory. This is a strange thing. This is 0. Okay, this is forget about this. And let's take moments about A. Okay. All right. Just a second. Just something. Okay, I will solve a problem. Maybe not today. So problem, but I'm not sure if I should do it today or next Monday because there might not be enough time. This is too, let me open a new page. And start a problem at least for a while. Let me just. This is a problem I have asked in some midterm some time ago. Again, this is a 4-bar mechanism. As I have told you, M2 equals M4 4. There is T2, which is unknown. These are given. Acceleration analysis is done. With an angle of 210 degrees, okay? Ignore gravity, it says. So what is this T2, if you want to find it? Okay. So actually a lot of things is done here. The accelerations, well, since M2 and M4 are 0, you don't need the accelerations of the links 2 and 4. You just need for link 3. So the inertia forces are Fi3 is like M3AG3 without the direction at least. It is 0.6 times 19.4. Yeah, by the way, this is good. So BG3, by the way, here you have G3 equals BG, which is 68. Alpha, this was alpha 1, 3 was clockwise, so this will be counterclockwise, and now 210 degrees would be something like this. This is AG3. So the FI3 would be opposite to that. And it makes 30 degrees with the horizontal. Okay. So it makes a 30 degrees with the horizontal. Okay, well, I won't be able to finish this problem anyway, so I can go with you. Block diagrams. Let me draw the free body diagrams and then I will stop. For link 2, it's a horizontal link. The red ones are the inertia forces. And finally, link 4. Well, note that link 4, this is link 3, this is link 4. Actually, this is a two-force number, okay? And it makes things much easier because if this is theta 1, 4, which can be found, we didn't, this is theta 1, 3, which is 60 degrees. This is given. Theta 1, 4 actually can be found to be, if I'm not wrong, 80 degrees. From trigonometry, you can find it. It's not too difficult. No, it cannot be 80 degrees. It's just 110. It's not 80, but it's just the complement of that, which is 110. Okay, so we have written them. Then we will write the equations for the unknowns and solve them. Actually, also note that the link 2 is a 2-4 plus 1m number. This makes things kind of simpler, okay? We are going to use these. Okay, let me stop here for today. We will continue this problem not on Wednesday, but next Monday. Okay, I'm going to start with this problem and solve some other problems next Monday. All right. Yeah, do you have any questions?